This week we will study the Fourier analysis, Fourier transformation, and in this lecture we will focus on deriving the Poisson summation formula, and along the line we can discuss the what is the connection between the Fourier analysis and the Fourier transformation and the complex analysis. Okay. So I will discuss also the philosophy when we move on. Formula as evaluation of series of values at integers of holomorphic function on horizontal strap with uniform horizontal quadratic decay. Okay, so before we do that, let's explain a little bit about the title. So in title, you see there are a lot of technical conditions like uniform horizontal quadratic decay and in the horizontal stripe. So that's the main difference between the geometry and the analysis. So in analysis, we will study the subtlety of the conditions. For example, if you learn Math 522, then we will have function. We have a lot of function spaces, LP space, L infinity space, and hard space, and WMP space, and kind of stuff. And also you can put on more technical decay condition, growth condition, and smoothness assumption, kind of, and then you study the operators and the solutions of PDEs, etc. So in this, condition is very important. So here, in this lecture, we're not going to do the optimal condition. We just use some not that strong condition, but still give you some idea the interplay between the complex analysis and the Fourier transformation. Okay, next we recall the Poisson summation. Formula, which is given by summation Fn from infinity, negative infinity to infinity, and then formula says this equals the summation of f hat n from negative infinity to infinity, where f hat c is an integration of fx from exponential negative 2 pi I cx dx. Okay, so here, before we move on, we need to explain a little bit. So the transformation, this is called Fourier transformation. And correspondingly, later on we will study the Fourier inverse transformation, which is given by f hat c exponential 2 pi I c x dx. And here negative infinity to infinity. And later on we will prove that to prove. Under certain condition, this is fx. That's called the Fourier Inversion Theorem. And remark 2 is, in physics, you use different notation for the Fourier transformation. So what does that mean? That means in physics, you use IPX, so you don't have P. And when you do integration, so this is now you are in momentum space, and then if you do the inversion transformation, here in physics you always assume the Fourier inversion theorem holds, or you assume function is good enough to perform all the operations, and then f hat p exponential IPX dx divided by 2 pi. I can't remember if I use px in the correct way, otherwise you need to interchange p and x. But basically, the point I want to make is, here in mathematics, you usually have 2 pi here. Okay, so the advantage is you don't have the coefficient. So Fourier transformation, inverse transformation only differs by minus sign in the index. The disadvantage is the index is a little bit complicated. But for the in the physics notation, the good point is you don't have pi over h kind of stuff here. So actually take h bar to be 1. So the index is kind of clean, but then the disadvantage is when you do Fourier inverse transformation, you have dp over 2 pi. So they're the same thing actually if you normalize your variable. But in this course or in mathematics, we just take the first convention. We use exponential 2 pi I cx. Okay, now let's look at the functions. Previously, we studied that if you have polynomial rational functions and the condition degree q greater than or equal to degree p plus 2, then we can take a contour, so which is a big box, to compute the summation. And here we want to mimic it, but under the weaker condition, we only know its quadratic decay along the horizontal direction. And also the function is only defined in a stripe with a little bit wise. So the contour we are going to take probably just a narrow rectangle along the axis, and which tends to positive real direction and the negative real infinity. So in other words, so above you consider positive negative n times 1 plus I. And here you consider positive, negative, n plus 1/2 plus minus IB. B is 2B is the width of the band. Okay. So there will be some technical issue doing Fourier transformation and the contour integral. So let's set up. Let fz be a holomorphic function on an open strap SA equals z complex number whose imaginary part is absolute value of the imaginary part is less than a. We define the family KLFA to be a set of all the functions which are holomorphic on SA and exists constant a greater than 0 such that your function decays along the x direction as a divided by 1 plus x squared for all points in the strap. And we take the union of all such functions. That means we can, as soon as you have a strap, no matter what size it is, you call it, you put it into the family KLF. So what does that mean? That means, remark, as soon as F is defined in a strap, it suffices to derive formulas. So the actual width of the strap is not that important. Of course, you need to put the quadratic decay condition. Then the theorem, which is Poisson. As I said before, you might have the Poisson summation formula and a weaker condition. So here we just carry out one form to get the idea. So for any f in the family KLF, we have the Poisson summation formula. And where f C is the Fourier transformation of fx. Okay, now let's prove the summation formula. Sorry, upstairs they are drilling. So we will compute this by the summation by evaluating a contour integral fz times exponential 2 pi iz minus 1 dz, and let n goes to infinity, where b is less than a greater than 0, and for all f in the family. So the actual factor, as we discussed before, just coupled with to pick out the information at the entry point via the residual theorem. Without a singularity, if you do contour integral, you just get a 0. So you need to prescribe some singularity. So that's so you have the concentration of the function. Okay, so the remark is 1 over exponential 2 pi I z minus 1, it's just like cotangent pi z or cosecant pi z. So has simple pole z equals n, where n is an integer, and the residue, if you do expansion, residue at z equals n is 1 over 2 pi I. So how to see this? You just expand the function near z equals n. Plus O z minus n squared. Okay, then you just pick out the coefficient of 1 over z minus n as your residue. And here, let's fix the notation for the contour. So this is a domain, and the contour is a rectangle, consists of 4 parts. So you have, for the vertical side, let's call it I1n, I2n, and the horizontal side, let's call it L inverse B n, and above you have LB n. Okay, then here B means the width of the strip. So this is m plus IB, m minus IB, minus m plus IB, minus m minus IB. Therefore, if you so look at the contour integral along CMB. So recall the CMB is L1n minus LBm plus L2m plus L negative Bn. Okay, if you do the contour integral fz divided by exponential 2 pi I z minus 1 dz, then you have the following. It's the limit when n goes to infinity, integration I1 n fz divided by exponential 2 pi I z minus 1 dz plus I2n, same thing, and plus L minus Bn fz exponential 2 pi I z minus 1 dz minus Lbn fz dz exponential 2 pi I z minus 1. So let's first estimate the vertical sides. This is easy by the quadratic decay condition dz. So the length of the interval is 2b, and then you have maximum fz z is here you need to avoid the pole of 1 over exponential 2 pi I z minus 1. Therefore, here you need to have m plus 1/2 plus ib, and here you have m plus 1/2 minus ib. Here you have negative m plus 1/2, negative m plus 1/2. Okay, so here 1 plus 1, m plus 1/2 plus it. T is from, okay, well, I write in this way. M plus 1/2 plus it. So t is from negative b to b, and then in the denominator, look at this one. So this is exponential 2 pi, we have I here, 2 pi I m plus 1/2 plus it minus 1. So this is exponential negative 2 pi t times exponential 2 pi m plus 1/2 I minus 1. Okay, then this will be so recall that the direction, so this is imaginary. Therefore, the absolute value of this will be less than or equal to 1 plus exponential negative 2 pi I so this is less than negative b squared plus 4 pi b, and then anyhow it's a constant, then the whole thing will be less than, because of the quadratic decay, constant times 1 over 1 plus n squared goes to 0 when n goes to infinity. And here n, this holds for I1n and I2n. There's no difference. Okay, now let's look at the integral along L minus Bn. We plug in the value for z. So here z is x minus bi. Therefore, you have integration from negative m plus 1/2 to m plus 1/2 fx minus bi divided by exponential 2 pi ix exponential 2 pi b minus 1. So let's call this limit integration of fz exponential 2 pi iz minus 1 dz on L inverse negative b. So intuitively, that's L inverse b just a horizontal line. with imaginary part a negative bi. So you are integrating on this imaginary number line. Sorry, you are integrating on this this line. Okay, next we want to do some estimate. Of course, first you need to show this is convergent. So claim the limit exists. Oh, this is because so if you take m plus 1/2, m prime plus 1/2, fx b minus bi norm divided by exponential 2 pi I x exponential 2 pi b minus 1 dx. So this will be less than or equal to integration from m plus 1/2 to m prime plus 1/2 a dx 1 plus x squared 1 over exponential 2 pi b minus 1. This goes to 0 when n prime goes to infinity. Then by Cauchy criteria, of course this is same for negative n prime goes to okay, so probably let me repeat this for negative part. Negative. You can do the similar estimate here. Goes to 0. Put this here and put this here. Negative infinity. Oh, yeah. When n prime goes to infinity. Therefore, by Cauchy's criterion, the limit exists. Similarly, we can show that the integral along LBN fz dz or fz dz divided by exponential 2 pi iz minus 1 exists. We denote it by the integral LB fz divided by exponential 2 pi iz minus 1 dz. Intuitively, just the integral along the line with the positive, with the imaginary part bi. Okay, now notice that exponential 2 pi iz norm of this function is exponential 2 pi ib less than 1 on LB. Then we have the following expansion, and from 0 to infinity exponential 2 pi I n z. So the convergence is uniform. Is uniform on LB. Why this is true? Because here the real part of z in the exponential contributes just a phase. The norm of exponential 2 pi I n z is bounded by e pi I n z is bounded by exponential negative 2 pi mb. So you have power n here. converges very fast. Okay, then similarly when we on the L negative B, then we have greater than 1 on L negative B. Therefore, when you do expansion, just like Laurent expansion, we need to first divide by 2 pi I z and then do the expansion with the negative power. I and z. The convergence is also uniformly on L inverse B. Then, so first, by the residual theorem, this equals the limit n goes to infinity, the contour integral of CMB fz divided by exponential 2 pi I z minus 1 dz, and this equals integral on LB, minus integral on LB, because the orientation fz exponential 2 pi I z minus 1 dz plus L inverse B integral of the same function dz. And then you use the expansion in the above. You see this is summation and from 1 to infinity. Because of the uniform convergence of the power series, you can change the order of summation and the integral. So this will be this and the plus n from 0 to infinity integral L B fz exponential 2 pi I nz dz. Okay, then you find this is exactly the summation of the Fourier transformation at integer points. So we are done with the proof of the Poisson summation formula. So in the following, we will prove the Fourier inversion theorem under some strong condition. So for f in so next time we will prove the Fourier inversion theorem in its full generality and a lot weaker condition. There's no holomorphic extension needed. We will discuss the relation there. Summation maybe it's whose Fourier transformation is f star c. Okay, I don't know if we prove that the Fourier transformation always exists for such functions. Yeah, we can prove it just in a moment. And fx equals the integral of f hat exponential 2 pi I c x d c. So proof. So first noted that since f has quadratic decay, so fx exponential negative 2 pi I c x dx Okay, so yeah, I would write down. It's not so rigorous, but rigorously you need to use the Cauchy criterion. But I think it's easy, so I write it very slow. This will be less than some constant times, because you have quadratic decay, so you have 1 over 1 plus x squared, negative infinity to positive infinity, dx. So this is bounded. Then f could see our f hat, then f hat exists. Okay, then before we prove the inversion theorem, Fourier inversion theorem, let's look at the idea roughly. So formal proof, we give a formal proof. See what's going on indeed. So f Cauchy exponential 2 pi I Cauchy from negative infinity to positive infinity, d Cauchy. Then we plug in the formula for f hat for the Fourier transformation. So this is actually u equals negative infinity to positive infinity fu exponential minus 2 pi I Cauchy u du exponential 2 pi I Cauchy x d Cauchy. Okay, then if you can change the order of the integral, you have fu integration of fu times integration for Cauchy from negative infinity to positive infinity exponential 2 pi I Cauchy x minus u d Cauchy du. And for the inside exponential function, if you are a physicist, then you know this is a delta function. Or explicitly, it will be I Cauchy x minus u divided by 2 pi I x minus u plus 2 minus infinity du. So this is actually delta function. Of course, mathematically, this does not make a lot of sense. If this is a delta function, then you know after integration is fx. Okay, so how to make sense of the delta function? So look at, suppose we split the integral to two parts. I mean for the green part, for this part, sorry, for the red part. So look at this half, exponential 2 pi I Cauchy x minus u d Cauchy. And you shift u a little bit up to u plus ib. Then what do you have? So if you know the, so assume we have the contour integral, then you know that if we shift a little bit, the integral should be the same. Okay, but now from the formula, if you still do the integration, then you have exponential divided by 2 pi I x minus u minus ib, and where Cauchy 0, Cauchy negative infinity. If you plug in 0 and negative infinity, now instead of have some 1 negative 1 always bouncing for the negative infinity part, because of this, so I Cauchy times negative ib is b Cauchy, so this is negative infinity, therefore you only have 0, so this gives you 1 over 2 pi I x minus u minus ib. So likewise, if you do the integration for Cauchy from 0 to infinity, e pi I Cauchy x minus u, we want to transform it to integration along the line a little bit lower, so u minus bi, and then you have e exponential divided by 2 pi I x minus u plus ib. Theta is positive infinity, theta is 0. And then you see this is negative 1 over 2 pi I x minus u plus ib. Okay, then if you look at the remaining integral, then what do you have? You have fu divided by, times 1 over 2 pi I x minus u minus ib minus 1 over 2 pi I x minus u plus ib. So what is this? If you look at the picture, this is the stripe we are in. Okay, then if you look at the picture, this integral just a horizontal path of the contour integral. Of course, you have two blue one missing. But when you take the limit, actually this will give you the this is the contour integral corresponds to the contour integral of fz divided by 2 pi I x minus z contour dz. Oh, here you have minus sign if you use a positive orientation. Then this is by Cauchy theorem. This is Cauchy integral formula. This is exactly. So here notice that the pole is at z equals x. This is fx. So that's the idea. Use complex analysis, especially the the contour integral. Using this technique, we transform the delta function in the Fourier transformation to a contour integral. The main technique is shifting the integral line by positive or negative by a certain imaginary number. Okay, so this idea actually comes from Lagrange and Amorphous when they studied the solution of the constant coefficient partial differential equation. So Fourier analysis is very efficient in solving the partial differential equations with constant coefficients. This is known to Fourier probably 300 years ago. But then the problem is how to rigorously prove this. If you restrict to the real world, people had a hard time to understand this until probably after 100 years after Fourier's work. Lagrange and Amorphous realized that if you shift the integral line by an imaginary number, then by the complex analysis method, you are able to prove rigorously the solution of the constant coefficients completely. So also combine their work and later on Homander's work, so the linear PDE with constant coefficients are well understood. So nobody right now, the mainstream is not doing the constant coefficients PDE. The mainstream is doing the nonlinear PDE. Okay, after Homander's 4 volumes book. Okay, so this is a little bit history. So now let's carry out the rigorous proof. So rigorous means, what do we mean by shift a line a little bit? So for f in this family and fix constant particle count b less than a, then we know that fx is given by the contour integral through the Cauchy integral formula. So here the loop C and B, let's repeat it. It starts from n plus 1 half plus bi n plus 1 half minus bi, and here you might don't need, probably you don't need 1 half, but don't hurt, we just keep the notation constant. And x you assume is less than n, therefore it's inside somewhere here. Okay, so this is the usual Cauchy integral formula. And notice that f has quadratic decay along horizontally. Therefore, just as what we did in the proof of the Poisson summation formula, the vertical part of the contour can be dropped when you take a limit, and also the horizontal line, the limit of the integration along the horizontal lines exists. Therefore, we can write fx is 1 over 2 pi I integration along L negative b f c d c divided by c minus x minus 1 over 2 pi I integration c, so here along LB f c d c minus x, so where x is a real number. Okay, as we showed before, because of the quadratic decay, f hat c exists, and which is defined by the Fourier transformation of fx. And then because of the quadratic decay, so here f Cauchy is negative infinity to positive infinity, u from negative infinity to positive infinity, fu minus ib exponential negative 2 pi I u minus ib Cauchy du. So when Cauchy is positive, so what does that mean? That means if you look at the picture, originally your Fourier transformation is on the real number line, but now you are going to integrate along L negative b. So we are saying this is the same. Why this is the same? Because your function is holomorphic along this contour, and because of the quadratic decay, the blue part, the vertical part, the integral along the vertical part goes to 0. So let's estimate I1n. So integration along I1n f z times exponential negative 2 pi I z times Cauchy dz. So let's estimate this part. If you plug in the coordinates, so here z will be n plus 1/2 plus it. So this will be less than integration y from negative b to 0. Sorry. Oh yes, f n plus 1/2 plus iy and times exponential negative 2 pi I x n plus 1/2 plus iy times Cauchy dy. This is the equal sign. Okay, and this will be less than or equal to constant times integration 1 over 1 plus x squared, and because of quadratic decay along the horizontal direction. And if you take so recall here Cauchy is a real number, it's positive. The Fourier inversion theorem, we prove it for the real variables, and therefore here it's 2 exponential 2 pi I y times Cauchy dy. Okay, and then the key point is because y is negative and Cauchy is positive, so there's no I. Y times Cauchy. This is less than or equal to 1. Okay, then you have estimate, and therefore when so here n squared. Therefore this goes to 0 as n goes to infinity. So that's a estimate. Therefore, as a conclusion, we know how to shift the line. So this is exactly what we mean by shifting lines. Okay, then if we look at the integration from 0 to positive infinity, f hat c exponential 2 pi I x c d c, then we can carry out exactly the previous intuitive proof, formal proof. We plug in the formula, and because of the fact that you have decay here, because here b is positive, and then you look at this one. This part, this is exponential negative 2 pi I u c minus 2 pi b c, which decay very fast for larger c, and this decays very fast for larger x. Therefore, the whole thing is absolutely integrable on the CU plane. Therefore, by Fourier theorem, you can change the order. So you can first integrate C and then U. Fu minus IB times integration 0 to C exponential negative 2 pi I U minus IB minus x c d c du. Okay, now just use previous computation. We know this is Fu minus IB times 1 over 2 pi I U minus IB minus x du. And this is exactly 1 over 2 pi I integral along L negative B f c minus x. Okay, similarly, when c less than 0, we can prove that f hat c by shifting a line, shifting the integral line to the up half plane. You have this. Here you use the fact c less than 0 to prove the vanishing of the horizontal lines. So the horizontal lines vanish because of the decay and the sign of c. Then, if you do the integration from negative infinity to 0, f hat c exponential 2 pi I x c d c. So similarly, you just write it out and exchange the order of integration. You have that this is integral from negative to infinity to positive infinity. Fu plus IB divided by 2 pi I U minus 2 pi I U plus BI minus X du, which is negative 1 over 2 pi I integral along LB f c minus x d c. Therefore, we prove that the integral of f c, you combine these two, exponential 2 pi I x c d c, equals the difference of these two line integral. But then we prove that this is exactly the f exactly fx from the Cauchy integral formula. Okay, then we are done with the Fourier transformation, inversion theorem. So please take time on this technique. If you are physicist, it's okay. You just view it as delta function. If you are mathematician, then you need to be careful the rigorousness. Okay, it really spends people a lot of time to find this proof. Okay, next time we will study the Pelewinner Theorem, which will connect the holomorphicity of the function to the decay of the Fourier analysis. So in principle, there's one sentence. Philosophically, the sentence is like this. The holomorphicity, the more you have the holomorphicity, the better you have the estimate. Okay, I will stop here.